Introduction to Doubly Linked List. So welcome everyone. We're going to look into doubly linked list. So we talked about in the singly linked list section, unlike arrays, a linked list are dynamic. And uh, one thing that is different about doubly linked list compared to singly linked list is that it adds an extra layer of flexibility by allowing us to traverse not only forward but backward as well. So we are able to traverse in both directions. So we will look at how this feature allows us to do things differently, how this feature sets them apart, and why it might be uh, better or advantageous in certain applications. So let's first look at the structure of a doubly linked list. Basically, each node in a doubly linked list is a self-contained unit, which is similar to singly linked list. Um, it has data, and next, I guess one thing that is different from singly linked list is that it has a prev, which is a pointer to the previous node. So this dual linkage is where we got the name doubly linked list, and this dual linkage allows us to move forward and backward through the list. So we have much more flexibility. And similar to the singly linked list, the head points to the first node, and while the tail points to the last, with the end points of the list pointing to null. For Python, it will be none. By the end pointing to null or none, it signals the list boundaries. Let's look at some operations on doubly linked list. For this slide, we will look at creation. So creating a doubly linked list begins with establishing both head and tail, and initially pointing to null. So when we add our first node, uh, we know that it becomes both a head and the tail since it's the sole element. And as we add more nodes, the list grows, maintaining its two-way connectivity. Now let's look at insertion. So insertion in a doubly linked list can occur in various places at the beginning, at the end, or in the middle. So when we are inserting, uh, we would need to first adjust pointers of neighboring nodes to maintain the list structure. And this operation kind of shows the list flexibility. We can easily add elements without reorganizing the entire structure, unlike an array. So let's look at the code example, insert at the beginning. So given this new data, we will first initialize a new node with data, and then we know that node not only has data, but also next and uh, prev. So we will first say that the new node next equals to self head. So we're inserting at the beginning. And if the self head is not none. This means that we already have node for this doubly linked list. Then we want to set the existing node self-head.prev to equal to this new node, then set self-head to new node. This way, we are maintaining a connection between the existing head with the new node, which will become a head. And uh, if the list is empty, then we will have self tail as none. We will just put tail as new node as well. Insert at end is very similar, except that we are doing the operation in the tail. So everything else is the same, except that we're using tail, then head. So let's look at deletion operation. So deletion, what we mean by deletion is that it's removing a node and relinking to its neighbors. So whether we're removing from the beginning, the end, or the middle, we have to be careful adjusting the pointers to preserve the list integrity. So I think one thing that is difficult with linked list is doing pointer manipulation and making sure to maintain the list structure. So just to see the example, delete from beginning. Uh, so we want to handle the case of the list being empty. If list is empty, then we just want to return. Otherwise, we would want to uh, change the head because we are removing the existing head. We want the next element to head to become the new head. And then we need to, now that we have this, uh, the neighboring element as head, if we want to set self head prev to be none, otherwise, we know that the list is gonna be empty. List has a one element. If that's the case, we will put self tail as none. So it's really important to handle all these uh, cases. Now let's look at traversal operation. Unlike singly linked list, traversal in a doubly linked list is unique because we can traverse in both directions, forward from the head to the tail and backward from the tail to the head. So this bi-directional traversal capability is useful in applications where reverse navigation is required. I guess one example we can think of it is a web browser's history. You sometimes want to navigate in a backward direction. So if we look at this code example, traverse forward, we will start from the head. So we will set current to be self.head, and then we will use while loop, and then we can just keep setting current to be the current next element. And we know that this will traverse until the end because when it reaches to the end, we know that we current next points to null or none. Therefore, this while loop will terminate. Similarly, traverse backward. we the code looks exactly the same, except that we're using self tail instead of self head, and we're uh, setting the current to be we're setting current prev to be current in the while loop. Now search operations. So searching in a doubly linked list involves sequentially moving through the nodes until we find the desired data. While the process is similar to that in a singly linked list, the ability to move backwards can be advantageous in some scenarios, and this could really reduce the search time. If we look at this code example, we will have search method, and then we have this target that we're trying to search. So we would put current as self head because we want to start from the head. And we will also have a while loop because, as you've seen from a traversal example, you have to go through element from the head or tail. We will check if the current data equals to target. If that's the case, we'll return true. Otherwise, we will continuously traverse by setting current next to be current, and while loop will terminate if this if current becomes none. So if the target data does not exist, then we'll return false. Now, update operations. So updating a node in a doubly linked list involves changing the data stored in one or more of its nodes. And this operations is straightforward since it doesn't involve modifying the list structure. So it's just modifying the data within a specific node. So we can see that this also uses this uh, while loop, and it tries to see if the current data matches the old value. If that's the case, then it replaces current data with new value. Advantages and disadvantages. So doubly linked list offers several advantages, I guess, compared to arrays, easy insertion and deletion, and compared to singly linked list, it offers bidirectional traversal. However, these come at the cost of additional memory overhead compared to singly linked list, because for every node you're storing another pointer, prev, and operations to maintain list structure is slightly more complex because you need to make sure to connect not only uh, next but also prev. So understanding these trade-offs is crucial when deciding whether to use a doubly linked list in your application. Use cases. So doubly linked lists are ideal for applications that requires frequent insertion and deletion operations, and also bidirectional traversal. They are often used in various real-world applications, uh, such as navigation systems, gaming, and managing browser history. And because of their flexibility and insertion deletion, it makes a powerful tool in a programmer's toolkit. So we looked at kind of implementation example throughout the slide. If we want to implement the whole thing, we would first want to define a node class, then create a doubly linked list class to manage the nodes. Then you want to uh, add those methods that you've seen for insertion, deletion, traversal, search. And best practices and common pitfall. So when working with doubly linked list, it is really important to manage the linked list structure and handle all the edge cases. You always want to remember empty list or single node list. So doing pointer manipulation carefully is key to avoiding common pitfalls such as memory leaks or corrupted list structures. Conclusion. So doubly linked lists are very dynamic data structure and offers advantages in some applications. So I encourage you to explore further and experiment with implementations and consider how they might solve problems in your own projects. Thank you for joining this session for on doubly linked list.